Yes. Hi, everybody. I don't know if they can see my face or just the whiteboard.
We also see you, yeah, in a corner of the
Ah,
screen. Yeah.
oh, great. Okay. So first of all, many apologies. I couldn't make it in person. There was just some emergency situation at home, and I had to get back. I was already at the airport, but I had to essentially turn around and go back home. That's one thing. Another thing is that, of course, being that it's on Zoom, it will be a little bit more difficult to keep it interactive. So if I can ask the students to make a small extra effort, if you have a question or comment, just make a small extra effort so that I can hear the question, and also your questions might be interesting to many other of your peers. So it would be good to discuss it and keep it interactive despite the circumstances. All right, so let's get into it. So the topics that I'm going to cover are semi-classical techniques or semi-classical methods. So let me just explain what is the idea of this topic. The idea of this topic is that there are many strongly interacting many-body quantum systems. By many-body quantum systems, you should think about quantum field theories with some very strong interactions between the particles. You can also think about condensed matter systems with very large interactions, very far from the quadratic approximation. And in these systems, we typically have very few non-perturbative tools. Some of them have to do with the topology of quantum fields, like anomalies and these kind of things. But also there is another set of tools, which are the semi-classical techniques that I'm going to explain. Now, of course, you might think that semi-classical techniques should be useless for strongly interacting systems because they're very far from the classical limit by definition. But the point is that I'm going to show you that um, in some situations, even in strongly interacting theories, there are some pieces of the theory that become effectively semi-classical. So some sectors may become perturbative, so to speak, or semi-classical perturbative. So qualitatively, the following might happen, and we'll see that this happens in many interesting systems. So even though h bar could be, let's say, large, h bar is usually one, but by h bar I mean some coupling constant in the theory. So h bar could be large, meaning not small, of order one, but it will sometimes happen that in the quantum states of the system that has many particles, so in states of the system, in states with many particles, or in states with could be also states with some large charge. We will see various examples of both. And this charge could even be a space-time charge. It doesn't have to be an internal charge. It could be states with many particles or large charge, or maybe large spin, large anything basically. Let me just see how to scroll down uh, the whiteboard. Just 1 second. I have a different whiteboard that I usually use. I have to understand how to scroll down in this one. Is that all it's giving me, this tiny amount of space? Could that be? Maybe that's all it's giving me. I'll just work with this small amount of space and I'll use the other whiteboard tomorrow. So in states with many particles or large charge or large spin, it would sometimes happen that even though the underlying system has a large H bar, there is an effective H bar. There is an effective H bar that is much smaller. So we will see the concept that sometimes there is an effective H bar which is like the original h bar divided by some quantum number. Let's call this quantum number q to some power. That the power depends a little bit on the implementation. And this would allow us to gain some non-perturbative insight into highly excited states. So we will be talking about highly excited states. We will be talking about highly excited states, and we will be able to gain some insight into highly excited states of strongly interacting systems. Now, why am I wasting your time with this idea? There are two reasons that I'm gonna waste your time with this idea. First of all, if there are any questions, just stop me, or maybe I'll stop for once in a while also asking if there are any questions. Are there any questions about the fact that a new effective H bar can emerge in highly excited states? Okay. So why am I wasting your time with this idea? So there are two main reasons. First of all, the semi-classical techniques around these highly excited states in many cases turn out to be extremely effective. This is like the magic usefulness of effective filter if you want. Sometimes you can just use those semi-classical techniques way beyond what they were meant to be doing for you, and it still works. That's of course not very convincing. It may or may not work. Another thing is that uh, there are many, many phases of matter which are semi-classical. So we know that theories could be approximately weakly coupled. They could be approximately maybe in a superfluid, in a Fermi surface, in a superconducting state. There are many interesting semi-classical physical states. These are like phases of matter, which are with a nice thermodynamic limit. So this kind of idea allows us to explore many semi-classical limits and ask which semi-classical limits actually exist. So it's like, the famous picture that there may be many, many weakly coupled limits to a given strongly coupled system. So by playing with these states with large quantum numbers, we can explore many interesting semi-classical limits. And finally, there is a lot of recent attempts to measure some excited states going beyond just small excitations. And so that developing the theory is very useful for that. So there are many reasons of that sort.
There's
Yes,
a question. If
yes, I'm
Hi,
listening.
yeah. Is it similar to keeping the n tends to infinite limit, but g square n is fixed?
Okay, that's an excellent question. Actually, the questions work out very well. I could hear very well, so don't be shy. Just ask whenever you have any question. So let me just erase that. First of all, I'll try to get my hang of this, or maybe this one. Okay, so I just erased everything. Hopefully that wasn't a big disaster. So indeed, let me tell you something maybe to whet your appetite a little bit. So one thing that you may have seen in your studies is that you can take in the theory of matrices, let's say in Yang-Mills theory, which is a theory of matrices which are n by n with some interaction, G. We know from the work of 't Hooft that there is a very interesting limit which is essentially semi-classical, where you take the matrix to be very large, but you keep the interactions very small, such that G squared n is fixed. Let's say this is in the Yang-Mills constant. In the Yang-Mills context, in string theory, we keep G string n fixed. Now, so this is one semi-classical limit, but let me just, for instance, one thing that we've learned over the couple of years is that even in SU2 gauge theory, you don't need to take large matrices. Even in SU2 gauge theories, if you look at states with particle number q, states with many, many particles in that theory, it turns out that there is a limit where you keep GQ squared fixed. And this turns into, and you send q to infinity. That's like a semi-class. It turns out that this is a semi-classical limit. And furthermore, it turns out that this limit has a Tuft-like expansion, so a planar expansion. Even though there was no large rank gauge theory. Okay. So sometimes semi-classical limits are very rich. They make contact with this kind of physics. So when you the message is that you can get large numbers from just going to many states with a large occupation number. So in the history of particle physics, people always looked for simplifying limits, small epsilon, large n, whatever you can do to gain some insight. And a recent realization is that you can take just some quantum numbers to be large, and there are very interesting semi-classical limits that can emerge. And then you can try to use them as an approximation. So even in SU2 gauge theory, we now know that under certain circumstances, you can just do you can resum you can resum the whole perturbation theory under these conditions, and you get something like a planar expansion. So here you could say that h bar becomes effectively the original h bar divided by q. Okay. Any other questions? Good. So what I'm going to do is to start from an example. I will start with an example, but this example by itself is a whole field of research of many of your colleagues in the physics department. This is the example is the topic of the example is called gases. It sounds very far from particle physics, but you'll see that it's not far at all. And it will be essentially identical to what we will discuss later about strongly interacting quantum field theories. So it's a very good example because A, you can put it on the computer if you don't believe the results. B, there are at least 2 Nobel Prizes in physics already in this field. And 3, it's very interesting. There is a lot of interesting phenomena that come out in this field. Okay, so that's the first topic I'm going to cover. That will essentially be the topic of today. And after we understand this topic, the rest will be easy. Okay, so let's start. This is just quantum mechanics. The setup here is just ordinary quantum mechanics. And we will be in 3+1 dimensions. It's just non-relativistic quantum mechanics from undergraduate. So we will discuss quantum particles. We will discuss quantum particles. Remember that in quantum mechanics, particles are not created or destroyed. So we can just fix the number of particles. These particles will be in some bucket. Let's say they will be trapped by some bucket. We will put them in some domain in space. I'll make it more precise in a few minutes. And these particles will be not free. If there are free bosons, these particles will be bosons. The particles will be bosons, but the particles will not be free. There will be a small interaction between them. And we will assume that the interaction is very, very short range. Short range means that the particles will come in contact only if they collide, essentially. They will feel each other's presence only if they actually collide, when the wave functions like literally overlap with each other. Okay, so classically you might think this is gonna be the classical intuition with weak short range interaction is what is gonna be your classical intuition? Maybe somebody can say, what do you expect from particles with extremely short range interactions in some big bucket? Let me just draw the bucket. So this is some big container. The bucket is a container. What do we expect? What would this do? Anybody in the audience? What happens in just ordinary particles inside a big bucket. I'm just doing an experiment if on Zoom somebody will respond or not. Hmm? No?
Any guess?
Yes, so very good. So this would just be a yeah, this is not a very good experiment. I should wait for questions rather than solicit ones because that uh, yeah, so classically this would just be an ideal gas. Yeah, it's just an ideal gas. It would be super boring. Namely, it will be all the way back to ninth grade or whatever. But you will see that quantum mechanically, it's the opposite of that. Quantum mechanically, bosons at, of course, at low temperatures, yes? We're going to be at zero temperature. The quantum effects become very important at zero temperature. And the bosons, even at very low density, you can ask how many bosons am I putting in the bucket? So even at extremely low temperatures, at extremely low density, it will be very low density. I'll discuss particles at low density. Sometimes it's called dilute in the technical literature, dilute gases. So if you go to zero temperatures, quantum particles behave very differently from classical particles, and even at very low densities of just a few 100,000 particles over a macroscopic bucket, which is, 15 order of magnitude lower than the typical density that you encounter in real life, uh, the phase of the system will be very different. The equation of state will not be ideal gas. The spectrum will not be of ideal gas. It will be very, very different. And our goal we will try to solve uh, for what the system does when there are many particles at small density. So we'll take some large quantum number limit to try to solve the problem. Okay, so now the mathematics. What is the definition of the problem mathematically? Let's do two particles just for concreteness. Let me write the Hamiltonian that we're trying to diagonalize for two particles for starters. So for two particles, we just have kinetic term for both particles. Okay. Then they might be inside a bucket. So the bucket will be represented by some potential that is affecting the particles independently of each other. So the bucket is represented by a potential for coordinate 1 plus some potential for coordinate 2. That's the bucket. So far, even I could solve this problem because it's just decoupled. You just need to find the one particle states. The problem becomes super interesting when you add some short range interaction. You add some short range interaction, which is a function of R1 minus R2. Okay, we have to specify what exact short range interaction are we adding. Okay, so let me just give you an example for what the short range interaction could be. So it's going to be infinite and repulsive. So the particles are going to just repel each other super strongly if they come into each other's, if they're in each other's phase. R1, 2 is the distance between 1 and 2. If this is smaller than some number A, they're just going to repel each other. Otherwise, nothing happens. They don't feel each other. Okay, this is the definition of the problem with two-body. Now, this problem is still solvable. So if you have insomnia today, you can try to solve this two-body problem. It's you go to the center of mass. You know the trick, right? You go to the center. Well, if you have a bucket, then you have axisymmetric symmetry. You try to solve the problem using the axisymmetric. Well, I think maybe in a bucket it would be actually unsolvable now that I think about it. But in infinite space without a bucket, you could find the scattering and the phase shifts by going to the center of mass. In a bucket, it still looks maybe it's difficult to solve. But it's something you can put on the computer by discretizing the Schrödinger problem, and you can try to find the spectrum. Is the problem clear? Okay. I'm moving on, so I have to clear. Maybe somebody in the audience knows if I can save it somehow. Is there a way to create another page? Or it's just giving me one? It's just giving me so little space to work with. Okay. Okay. So we go next. In this short range potential, um, I want to simplify it just a little bit more. So the short range potential means that the particles come into interaction when they're very close to each other. But I want to simplify it one more step by one more step. So when you send a wave, when these two particles interact, they can come in at various angular momenta. So let me just try to draw a picture. This particle is coming in, this particle is going here, okay? So this particle is going this way, this particle is going that way, and then they interact if they come within a distance a of each other. They interact if they come to a small distance within each other. But they could be in various angular momentum modes. They could be in relative angular momentum L. Now, a very important point is intuitively obvious. If the angular momentum is very large, they will almost never interact because of the centrifugal force that will just push them from each other. And then they will never just interact. So it's very clear that the type of potential that we chose leads to very small interactions for high angular momentum, relative angular momentum particles. And what we want to do is a very common approximation in nuclear physics. It came from nuclear physics. It was invented by a famous Italian called, can somebody guess? So in the context of nuclear physics, Fermi invented a very important approximation that has been dominating the field of atomic and molecular physics, and it has been dominating nuclear physics. So Fermi invented an approximation where the potential is only affecting the zero angular momentum mode. He understood that short range potentials don't affect high angular momentum modes. And then he invented the potential which affects strictly mathematically only the zero angular momentum mode. So let me explain in equations. The potential that I told you on the previous slide, which was short range, just a hard barrier, leads to a phase shift. This is the phase shift. It leads to a phase shift which goes like the momentum times this distance scale that we called A to the power 2L plus 1 up to combinatorial factors. I can write them here just for completeness. That's what you would find for the phase shift, which is essentially the interaction strength for the potential that I wrote in the previous slide, which since disappeared. That's what you would find, and very clearly from this formula, that if the angular momentum is large, there's a lot of sun here. It's very clear that if the angular momentum is very large, then this dies off very quickly for low momentum scattering, of course. If you send the particles with very high momentum, they can penetrate even at high angular momentum. But if you look at the low lying, you want to understand the particles with small momentum, low energy physics, so to speak, this dies off very quickly. This dies off exponentially. as a function of angular momentum. So Fermi understood that it's useful to invent a mathematical formalism for a system where there is only scattering in L equals 0. So Fermi invented a potential. Fermi invented a special potential where delta 0 is minus Ka. Okay, so he took just the answer for L equals 0 from, oh, there is a minus sign. Oh my God, I forgot. There is a very important minus sign in the phase shift. You get minus sign in phase shifts when it's a repulsive interaction. I forgot. So negative phase shift is repulsive, positive phase shift is attractive, remember. So Fermi invented the potential where there is a scattering in the S wave, but all the other, scattering phases for all the non-zero angular momentum identically vanish. So Fermi invented such a potential. It's kind of a small lie to say that it's a potential. In AMO physics and in nuclear physics, people don't call it a potential, they call it a pseudo-potential. The reason they call it a pseudo-potential is because one cannot really write a formula for this potential. You have to take a scaling limit of a sequence of potentials with some conditions, and you get something like a pseudo-potential. It's a distribution more than an actual potential. It's not a delta function, though. It's actually a derivative of a delta function. It's some kind of distribution. Okay, so it's a very popular approximation for dilute gases and for nuclear physics to assume that particles interact in this way, for instance, for pions, etc. So that's what we will assume. We will assume that we have particles in a bucket at 0 temperature interacting with the Fermi pseudopotential, where only scattering at the 0 angular momentum channel can occur. Okay, now I'll write the main equation. Are there any questions about the setup? So we will try to solve this problem of particles in a bucket with these conditions. Yes?
I have a doubt. We could have had the numerator times e to the power of minus L, something like that also.
Yes, but that will not lead to identically vanishing phase shift. It would lead to a phase shift that decays very quickly. Yes? That's what you meant?
Yeah. Why this
Yeah.
particular form?
Hmm?
Why should we have a form of this kind? Exactly of this kind?
Okay, so there are two answers to that question. First of all, it turns out that you can ask, is the Fermi approximation good? That's what you're asking in a way, right?
Yes.
First of all, it's clear that what Fermi invented is a simplification because you should only worry about the particles coming into interaction if they come with relative angular momentum 0. Otherwise, you don't care about this interaction. So it's clearly a simplification. That's point number one. Point number two is that it's a good simplification because it's very close to what happens in real life for slow neutrons or for very low energy atoms in atomic and molecular physics.
Okay. Okay.
Thirdly, it's a technically good approximation in the sense of particle physics because it turns out that if you want, you will see soon that I'll write an action for n particles living in a bucket. It turns out that the higher phase shifts are irrelevant operators in the RG sense. Let me write it. You'll see that in some situations, these are irrelevant. Not the particles, I meant the phase shift. Interactions in this channel are irrelevant in the RG sense in many, many cases. So even if they exist, if you go to sufficiently low momentum, they really drop out from everything. You can neglect them. For instance, that happens for slow neutrons. For slow
Okay.
neutrons, it's irrelevant in a very precise mathematical sense, in the sense of their normalization group, that you can really just drop it if you're interested in very slow neutrons.
Okay. Okay. Yeah. Thank you.
Yes, I mean, of course, Fermi didn't know any of that, but it seemed like a good approximation to him, so he just did that. Any other questions? Now we're ready to write an action, finally. We want to solve this problem of particles with this very interesting very weak interaction uh, at zero temperature. So now finally we write an action. I want to remind you that in quantum mechanics there are two formalisms. One is a Hamiltonian. I already wrote the Hamiltonian for two particles. I could similarly write a Hamiltonian for n particles. It's basically the same thing. But there is another formalism which is called a second quantization. That's more like quantum field theory, but for non-relativistic particles. So the only thing is that the kinetic term, the time derivative is first order, not second order. So I'll be using that formalism because in that
Hi,
formalism,
I have a
yes,
question. Yeah, so
yes.
about the comment on irrelevant case. So you mean the interaction potential is some kind of a defect in the theory, and then
The pseudo potential is what in the theory?
defect.
Defect, no. No, why defect? It's these particles are moving. They are not stationary. They are not defects.
Then
I just meant that the interaction. You know phi to the fourth theory, for instance, right?
yeah,
Relativistic phi to the fourth theory. You could ask why don't we add phi 4 with 7 derivatives? Why don't we add it to the action? The
because
answer is that it's irrelevant in the infrared. So similarly, if you go beyond the Fermi pseudopotential, all the higher angular momentum mode interactions are irrelevant in that technical sense.
I see what you mean. Okay, thanks.
I'll actually write an action now. As I was saying, in quantum mechanics, a second quantization is a good idea. It just allows you to discuss. In quantum mechanics, we could either fix the number of particles and just solve the Hamiltonian on the computer, or we could just write an action that allows us to play, that allows us at the same time to study any number of particles. Of course, there is still no particle creation. There is a conservation number for the number of particles, but we can at least embed all the quantum mechanical instances with n particles into one bigger theory. So I'll be using that formalism. So I'll write an action. So it will be a first order in time derivatives action in 3 plus 1 dimensions. So we have dx3 dt, and now comes the kinetic term. I'll keep the h bar, by the way, in these lectures, at least in the first part about cold gases, I'll keep h bar. But when we switch to QFT next time, I'll get rid of h bar. Okay, so this is the main thing that's different from relativistic theories. Time derivative is of the first order because Hamiltonian is the first derivative in time in non-relativistic quantum mechanics. And then we have the usual kinetic term. That's a weird choice of sign. I'll put plus here. And then I have h bar squared 2m nabla squared. This is the trap or the bucket. So instead of calling it a bucket, I'm calling it a trap now. It's some potential, which is a function of r that, let's say, could model some bucket or some container, and that's multiplying psi. And sorry, there is a minus sign here. Let me just fix the sign. Is because the Laplacian has negative eigenvalues, so the potential also has to have a minus sign in front of it. And then finally comes the interaction. The interaction, finally. The interaction will have some strength G. I'll explain what G is. And by saying that there is scattering only in the S wave, what it means is that there is only an interaction without any derivatives. And now I'll just have to tell you what is this new coupling constant G. So that's a quartic interaction. It's very similar to the phi to the fourth theory. So this G is connected. G is connected to what we discussed before. It's the scattering length in the Fermi pseudopotential. So if you need to work out the pi's by asking what is the scattering phase shift that this model predicts compared to minus Ka, and you'll find that G is 4 pi h bar squared over n times little a. So essentially, if you think about h bar and mass as dimensionless, which is kind of convenient, then G has dimensions of length, scattering length. And that also explains why higher derivatives are irrelevant, because G is already irrelevant. So like G is the leading irrelevant operator. The ones which have even more derivatives are even more irrelevant. So we're just keeping the leading irrelevant operator in the sense of quantum field theory. But of course, in quantum mechanics, we also have a conserved particle number, which comes from integrating the field operator over space. So an irrelevant operator doesn't strictly go to zero because psi cannot go to zero. We have a fixed particle number. Okay, so this is the setup. It's in 3 plus 1. It's very important that it's in 3 plus 1. In 2 plus 1, G has some logarithmic renormalization, like there is some one lobe beta function, and the situation is a little bit more interesting. 3 plus 1 is the case where most of the experiments are, and it's a little bit more conceptually easy. There are no logarithms, and G is just a scale with the units of distance. Okay? So this is the problem. You might say it's a hopeless problem because it's a quartically interacting field. So that's why I'm teaching this subject, because you'll see now that with some simple manipulations, we will be able to understand the spectrum of this quantum many-body problem of particles in a bucket, at least in the limit of many particles, but still in the dilute approximation. So is the setup clear? This is the problem that we're going to be studying. It's in the second quantized formalism. Psi is adding particles. Psi dagger adds particles. Psi subtracts particles from the bucket. And if you fix the number of particles, you can just try to solve it in the Hamiltonian formulation. Are there any questions about this formalism? Okay. We are interested in finding the spectrum of the corresponding Hamiltonian, but we don't really hope to be able to do it for 3 particles. That would be quite insane to do it exactly. So we're going to try to find the spectrum approximately. There is no hope to solving this problem exactly. And we're going to try to find it approximately for many particles in the bucket. Let's say we'll see the dimensions. We'll have a bucket which is big enough, and there will be like 100,000 particles in the bucket, and we will be able to find the spectrum of the Hamiltonian by using semi-classical techniques, even though the 3-body problem is not solvable. Or maybe even the 2-body is too difficult if there is a trap. So that's our goal. So now the most important part will come. I'll show you how the effective H bar can change if you have many particles in the bucket. Are there any questions before I go to that?
Hi. So if the bucket is large and it can contain this really large n, but it is large respect to these n's, does it mean that we would then interpret the trap potential as like boundary condition on the field?
Yes. You can get rid of this trap if for instance your trap is just a container like that, and there is no, sometimes in optics people trap particles by a harmonic potential or some anharmonic potential. But if your trap is literally a container like a bucket, then you don't need V trap. You just V trap is 0 for R smaller than some capital R, right? This is R. And V trap is infinite for R bigger than capital R. And then what you do is you get rid of this V trap term in the action, and you just put boundary conditions, it just turns into Dirichlet boundary conditions on the field operator, which is the field operator vanishes on the boundary. Is that what you asked?
Yes.
Yeah. So that's what we will do actually in the first part, because that's the easiest system to solve. If the trap is harmonic or even unharmonic, the problem becomes a little bit more messy, but still, it becomes semi-classical when there are many particles.
Thank you very much.
Any other good questions like that? Or worse questions or better questions? Okay. I'm clearing these slides because I don't know how to save them. I'm just gonna quickly make the point now. I'll just quickly copy that, and so that you can see the main point of how we are going to simplify the problem a little bit. I'm eliminating the trap because we will think about the container with boundary conditions like before. So I'm just gonna eliminate it. And then I have this coupling constant G, and then I have psi dagger squared psi squared. Okay, so now the number of particles as before is this. So we're going to do a change of variables. So we're going to do a change of variables. The change of variables is going to be as follows. We will take psi and we will multiply it by square root of n, and we will call this a new field operator, psi prime. That will be step number one. There will be two steps. Step number one is going to be to do this change of variables. So let's do that quickly. We will obtain an action which, I should have put 1 over h bar here. Let me put it so you can really follow where the h bar is. There is an h bar in the normalization of the action. So now I have n, and now I have d3x dt, and the action simplifies a little bit. Okay. And now I have some g prime. I'll explain what is this g prime and how to think about it. By the way, I'm not using psi tag anymore. I defined psi tag, but I'm not using psi tag. It will just clutter all the equations beyond hope. And I just keep using psi even though I changed the normalization. And the most important thing now is that the wave function is normalized with 1. So the number of particles. So, and okay, I have to say what is g prime also, just for good measure. Let me just write the formula for g prime. So g prime. Oh. Oh. I'll do one more step in real time. Let me just do one more small step before I write g prime. So I'm gonna change the power of h bar here to 1, and I'm gonna remove this h bar completely. And I'm gonna fix the previous equation, which nobody told me was wrong. There is no h bar here because I already had h bar in the kinetic term. Just a second. I'll just fix the equations that you'll get. And now this equation is correct. Now everything is supposed to be correct, I believe. So then G prime is G. This is now Gn over h bar. And using the scattering length A, this is 4 pi h bar Na over m. That's step number 1. Now we're going to step number 2. Are there any questions about step number 1? It's just a trivial change of variables. So already in step number 1, something interesting happens. N, which is the number of particles, is no longer in the field operator. It's like an effective h bar. It makes h bar effectively it makes the theory effectively much more weakly coupled than before. I still feel that there is some weirdness going on with the h bars. I wish I could see it in real time. Let me try to fix the weirdness with h bar. Yes, I think actually it's correct now. So my convention is that the path integral you integrate. My convention is that in the path integral you put the exponential of the action divided by h bar. So I think in this convention everything I wrote is correct. Okay, so in step number 2, we do one more little observation, which is that we have the size of the bucket. So this condition that the wave function is normalized to 1 is nicer than before, maybe because it doesn't have an explicit factor of n, but it's kind of maybe slightly inconvenient because we still have the volume of the space. So that's a parameter. And the idea is maybe we should be able to remove it in the same way as we removed the number of particles. So the second step is to normalize the wave function and the coordinates in such a way that the volume of space becomes a dimensionless parameter. That would help us understand the physics a little bit more cleanly. So the second step is that I'll define the coordinates x. X will be a volume to the power 1/3 times some x prime. Okay, so I'm basically defining a dimensionless x prime by multiplying it by the volume of this. We're putting the particles inside some big ball of radius r. And so I'm just normalizing it like that. And at the same time, the wave function will be defined to be volume to the power -1/3 times psi prime again. In that way, the normalization of the wave function will stay the same, but now x prime is just dimensionless and goes from 0 to 1. So you repeat this exercise and you find 1 over h bar action equals to n d3x dt. I'm not going to use psi prime again. I'm just going to use psi, not to clutter the equations. So it almost doesn't do anything what I just did, but it's very crucial, as you'll see in a second. And here we get g twiddle now. Sorry, g twiddle. Oh no, don't do that. We get g twiddle. And then we get psi dagger squared, psi squared. And now, g twiddle, let me just write the final formula. Here, the normalization of the wave function is 1 equals d3x psi dagger psi. But now space has volume 1, so there is no parameters anymore. The dimension of space is not a parameter anymore. It's just 1. And g twiddle is given by, let me just get it right. G twiddle is given by, it's essentially G prime. G twiddle is essentially like G prime, but divided by the volume of the space. Because there are 4 psi's in the last term, so G prime became G divided by the volume of space to some power. Let me get the power straight.
Is the volume of psi and psi prime correct, the volume factor there? Should it be volume to the power -1/2?
Oh yeah, my God. Yes, that's why I got almost a heart attack now. The minus thirds were giving me trouble, yes. I'm trying to do it in real time to mimic an actual lecture. So sometimes make mistakes. Sorry. Yes, thank you very much. This should be 2. So that in such a way that the wave function is normalized correctly. So then G twiddle is 4 pi h bar, but now the number of particles turns into the density of particles. Now that's much better because we don't want to care about the actual number of particles. We want to care about their density inside the bucket. So we get the density of particles times little a divided by the mass. And this is where the physics will get. Now we'll make contact with actual situations in nature, unless there are questions. Are there questions about these trivial changes of variables? No questions. Or are no questions about these changes of variables? We move on. I wish I could keep. I'll just erase the. I'll just erase the all this. I just want to keep the last equation. Let's see if this is feasible. Not very convenient. Yeah, that way at least I'll keep the last equation. Saves me a little bit of time. Okay. So this parameter, just get rid of this one. This parameter NA that we encountered, which is the product of the interaction range. Remember, little a is the interaction range essentially. This product of the little n times a, it's a very important scale in nuclear physics and also in atomic physics. It's the product of the density of the atoms, or the density of neutrons if you're a nuclear physicist, and the interaction length. So what are the dimensions of this object? So little n is the number of particles per unit volume. Little a is an interaction scale, so it's the size of the region into which the particles have to enter to feel each other. So therefore, this has dimensions of 1 by distance squared. And therefore, if we take the minus square root of that, we get an interesting scale in the problem. And that's a very important scale. It's called the healing length. That scale is called the healing size or the healing length. Why do people call it the healing length? You'll see that the system in the semi-classical limit has some excitations, and this is the characteristic size of this excitation. This will be the characteristic size. Characteristic size of some excitations that we will encounter later. Okay, and the people call it the healing length because it's an excitation, and that's its size. So after that size scale, the system goes back to its ground state. So that's why it's called healing in the literature. Okay, so here are some examples to make it a little bit more connected to real life. So let's consider sodium. That's one of the most common cold gases. So people can cool sodium 23 to essentially zero temperature, and they can throw it into some container, and they can watch what it does. This is a landmark experiment that gave a Nobel Prize a few years ago. It was done, I think, in Colorado and MIT. Two groups did it at the same time. I might be getting it wrong. And the parameters in that experiment were the following. So I'm just gonna make contact with the parameters that I already defined for you guys. So the interaction range for sodium atoms. Can somebody guess the order of magnitude? Let's see if somebody guesses. What do you expect is the interactions range between two sodium atoms? In meters, let's say. Anybody has any guess?
10 to the minus 7 meters around
10
that.
to the minus 7?
Yes,
I
that
mean
was
that, yeah, well, the size of a sodium atom is like 10 to the minus 9, 10 to the minus 10. They don't really have any long range interactions. These are neutral atoms. Yeah. These are completely neutral atoms. So it's actually 2.7 times 10 to the minus 9 meters. It's super short range. They just have to collide head on to feel each other. And then the mass, well, I used capital letter for the mass, I guess. Did I? Yes. The mass of sodium atoms is just like 23 times the mass of a proton. So it's like that. Sorry, not 20. Yeah. And then the density. So the density is the density that's achieved in laboratories. It's extremely dilute. It's 10 to the 20 in a cubic meter. You might remember the typical density in terms of molecules per meter cubed of realistic materials. It's through the through the Avogadro number, and this is tiny, tiny, tiny compared to that. So these are extremely dilute gases. That's their density, and you can calculate the healing lengths. That's the size of an excitation that we will encounter. You can just calculate it from the formulas I gave you, and you get this. That's actually a pretty large scale if you think about it for an excitation. Okay, so these are parameters. Also, there is the size of the bucket. You can ask how many actual particles did people put in the container. So the size of the bucket is microscopic, and I think there are 100,000 particles or something in the bucket that this experiment was done in. So I'm just remember, I'll put it in parentheses. I think in the actual experiment there were 10 to the 5 to 10 to the 6 actual particles. So the bucket was very small. Okay, so this is the quantum problem that we're trying to solve. Now comes the concept. This is just technicality. Now comes the conceptual point. This is maybe the most difficult point to understand in this field, and even experts are confused about it from experience. So we were able to look at this equation now, back at this equation. We were able to take the number of particles outside of the action. And remember that when we put the thing into the path integral, we put 1 by h bar in front of the action. So therefore, we can immediately read out h bar effective. In this theory, it's 1 by n. So when we had many particles in the bucket, essentially h bar has been reduced to a tiny, tiny number. Is that clear? And you would think that therefore, when there are many, many particles in the bucket, we can just solve the problem using semi-classics. This is correct. Semi-classics becomes correct. When there are 100,000 particles in the bucket, semi-classical techniques become completely correct. With a small caveat that I have to explain. So remarkably, this quantum problem becomes essentially classical because when I do the path integral, I don't need to worry about quantum fluctuations. I just treat the operator inside the parentheses here. I just treat this operator as a classical differential equation and I look for the saddle points, which everybody knows how to do. There is one small caveat, which is that for this to make physical sense, the only place where capital N has to appear is outside of the action. Because if N appears also inside the action, then you don't really know what's a effective H bar, right? You don't really know what's the effective H bar because N appears in many places and there could be issues. And indeed, N appears inside the definition of Jit-Whittle because Jit-Whittle depends on the density of the particles. And the density of the particles increases if you increase N. So why can we use the semi-classical techniques? And this is the deepest point of this discussion. So the theory of dilute gases and semi-classics makes sense in a double scaling limit. The double scaling limit is where the healing length is kept fixed and the number of particles goes to infinity, or alternatively, the interaction range goes to 0. So the theory of dilute gases, or this Hamiltonian problem of short-range interactions, becomes essentially classical when we can use partial differential equations and solve it. If we imagine that somehow the healing length is fixed and A goes to 0 and N goes to infinity. And that really becomes the true to God semi-classical quantum problem, which we can use saddle point approximations for. This sounds incredibly unphysical because what does it mean to send A to 0 for gases? Like God gave us the atom of sodium and that's it. We cannot take sodium and change the interaction length. It's just a property of sodium. So we have to imagine a sequence of atoms, if such a thing makes sense, where A becomes smaller and smaller, but the density becomes larger and larger. Of course, we don't have such a thing in nature, but we just solve this mathematical problem, imagining that a double scaling limit exists. And then we take an atom like sodium and plug the results and forget. Plug and forget, hoping that this is within hoping that sodium would be a good approximation. That the solution to the double scaling limit is a good approximation to the sodium atom. Because indeed, in the sodium atom, maybe the healing length is not large compared to the size of the bucket, etc., etc. So it should make sense. Okay, so is the logic clear? This may be the most confusing point about this field, that you have to think about a sequence of atoms which fall into a double scaling limit. And then you can use semi-classical techniques. Are there any questions about this? Okay, good. So now we will look for our first semi-classical solution. Now I'll tell you about the simplest semi-classical solution. And okay, so the corresponding differential equation is derived from the action by the variational principle. So we obtain the classical differential equation from deriving the action. We take the action, and we take a functional derivative with respect to psi and put it to 0. That leads to a classical differential equation. I'll just write it schematically. You guys, as a small homework problem, can try to get the coefficients straight. So schematically, we get the differential equation that psi dot. I'll just write it schematically without any sign, worrying about the signs. We get some term like that. There is an I between them, very importantly. And then we get some cubic term, which is like psi dagger psi squared. And there is some g twiddle, maybe, or g prime, depending if we use the previous convention or the new convention. Let me just switch to g prime, so that the integral of psi squared will be, I'll use g twiddle. It will be better. We use this convention. Okay. It's a nonlinear classical differential equation. And maybe somebody knows the name of this equation in the audience. What's the name of this equation? Oh, very good. But this is not quite Gross-Pitevsky. This is the time-dependent Gross-Pitevsky. Yes. This is the time-dependent Gross-Pitevsky equation. Usually it's presented as the fundamental equation of cold gases. I spent like an hour explaining to you that that's completely false. Now you understand the foundations of this equation. It comes from assuming a Fermi pseudopotential and taking a double scaling limit in the space of atoms, which doesn't really make sense. Only then you can justify this equation. I hope this was a useful clarification of what is the regime of validity of this equation. Now, what is the simplest solution of this equation? Who can guess the simplest possible solution of this equation? With the constraint, don't forget the constraint ever. The constraint is psi dagger, psi is 1. So if somebody says that the solution is 0, that doesn't count as a solution. Because we have to have n particles. By the way, there is no more n. So a solution doesn't know about the number of particles. It's hidden inside G twiddle through the healing lengths. So what's the simplest possible solution you can imagine? Let's say that it will be extremely difficult to find an actual solution in a trap. Let's just ignore the trap. I'll write a solution that is a good approximation. Okay, let me just draw a picture and I'll give you the solution. I'll write a solution that's kind of valid here. Of course, near the trap, you have to make sure the solution quickly goes to 0. This happens over some very short distance scale, which is of order of the healing lengths. Outside of that boundary condition, there is a simple solution, which is the following. To find an exact solution in the trap maybe is kind of a nasty problem. But if you ignore that, you can imagine maybe infinite space with very large volume. If you ignore that, then the solution is just, let me just go back to G prime 1 second. It will be a little bit more convenient. You can see the factors of the volume. I'll put G prime. That's before I changed psi into the volume. Okay, so now we have a space. We have a bucket of size capital R. It's some circular volume. The volume of this bucket is R cubed. I'm just drawing it as a cylinder, but I'm imagining a bucket which is just spherical. So the wave function is 1 by square root of the volume times e to the minus I mu t. This is the simplest possible solution where mu is related to the density. So mu is not a free parameter. You have to satisfy the nonlinear Gross-Pitevsky equation. So therefore you have to balance this cubic interaction with the time derivative. Therefore mu is not a free parameter. It's G prime by V. Okay? This is the simplest possible solution. What does it describe? It describes a more or less constant density of these dilute particles. The density is space independent. The density is little n. And we ignored the actual boundary conditions on the sphere in which the particles are contained. That would require solving the full nonlinear equation, which is ms. And also, you can make an argument if you want to try at home that it actually modifies the solution only very close to the sphere, to the boundary of the ball, so on the boundary sphere. So more or less everywhere in the bulk, that would be the correct solution of the nonlinear equation. Okay, so this is the simplest solution. It describes a homogeneous dilute gas. This is just homogeneous dilute gas. You could say that we found the ground state of this quantum system, if you want to be super pompous about it and fancy. We found the ground state of the quantum system. We can now use this ground state to calculate the energy of the ground state by just shoving it into the Hamiltonian. And then we can look at the small excitations around the ground state. That's the most important exercise now. Is it clear what we're doing, or the big picture? We're still trying to solve that quantum problem. Now we have the ground state. We're going to try to calculate the ground state energy. We'll actually calculate some thermodynamic properties of the ground state energy, and then we'll try to calculate the excitations. By using semi-classical techniques, we will not have to calculate strongly coupled quantum systems anymore. It will all be semi-classical by expansion around the saddle point. Are there any questions about that? Good. Remove that.
Hi, I have a question.
Yes.
Because all of this machinery we're using does produce results, are there techniques or ways then to extend these results outside the special validity region?
To what regime do you want to extend them, for instance?
Well, for example, not n to infinity, but large n, but like in smaller with respect to a second scale we can introduce, or g being not really, really small, but still small, but less than what we consider here.
Yes, but that would require calculating loop corrections, right? It would be like weakly coupled, but not quite semi-classical. So you could do an expansion. I'm just presenting you with the leading answers, which is like the saddle point and the fluctuations around the saddle point. But you could do then an expansion. You could maybe even do something more ambitious like resurgence. Maybe you can do something that goes to strong coupling.
So in the case of resurgence, then we can also infer something about non-perturbative contributions.
Yes, for sure. For sure. And there could be super interesting things going on there.
Thanks a lot.
Yes, my goal is to just present you with the basic technique and apply it to various interesting systems. First, it will be cold gases, and then it will be quantum field theory and conformal field theory. And these things can be extended in probably many ways. Now, first, we found the ground state of a quantum system. You should be impressed because the Hamiltonian is not solvable, of course. So we can now calculate some properties of it. So first of all, what is the energy of this ground state? Let's calculate the energy of the ground state. How do I calculate the energy of a ground state? I start from the action. I open whatever book on QFT you like, and I find the Hamiltonian. I'm in the classical limit now. I find the Hamiltonian, I shove this wave function into the Hamiltonian, and I read out the energy. If you do this, you will find that the energy goes like Gn, up to some prefactors that you can fix it in your free time. So the energy goes like the original scattering range. G is basically up to h bars, the original scattering length, times the density. That's a formula for the energy. Actually, this is trivial. Well, let me qualify that. So it's trivial and non-trivial in two ways. So in what sense is it trivial? If the particles were not interacting, you just ignore their interaction, you would expect the energy to scale with the number of particles, right? And indeed, that's what we see. The energy scales with the density. So the dependence on density looks like you would pretty much get the same thing, uh, even if the particles were non-interacting, right? So that part is extremely obvious that the energy should depend like that on the density if there were no interactions. The thing that is remarkable here and completely counterintuitive is this, the prefactor, G. Where the hell did that come from? So we see that the energy has the scattering range inside. And okay, that's very interesting. This leads to some interesting. This cannot be explained in any way, which is like intuitive to me. Okay. Well, let me try to give you an explanation of why the interaction range entered into the energy. If the interaction range was zero, then all these particles would have been free, and we kind of ignored the walls, right? We kind of took the walls of this sphere to be very far away, and the particles are just behaving like free particles in infinite space. In that case, the ground state of the particle is just at zero energy. You remember that for free particles without interaction, the energy is k squared? Well, by 2m times h bar. And now we basically took the large volume limit, and this just goes to zero in the ground state. So if we did not have interactions, the energy would go to zero. So the correct answer for in the infinite volume limit without interactions is that the energy goes to zero. Here we found that the energy behaves extensively and that it's proportional to the interaction length. So in that way, you could make sense of it, that it deviates from free particles only by something that's proportional to the interaction strength, and then it's also linear in the number of particles. So that's very different from what you'd get for free particles already. And this changes completely the behavior of the ground state to perturbations because, for instance, let's take a derivative of the energy with respect to volume. This is also known as pressure. This is also known as the pressure of the ground state. It's just measuring how much energy you have to invest to change where the walls are. Okay, and that's given by n squared times g. Okay, and the speed of sound is the derivative of the pressure with respect to the density. I'm just quoting some results that you might remember. And that's proportional. That's proportional to Gn. So we see that this system behaves very differently from non-interacting bosons. Non-interacting bosons would have a vanishing ground state energy. Here, the ground state energy is proportional to the density times the interaction range. And it has sound. It has a speed of sound, which is Gn. This will be a very important quantity. Remember that G was proportional to the interaction range. So therefore, this is the same as Xi to some power, which is -2, I believe. So therefore, we obtain that the speed of sound is the healing length inverse. So we see that the fact that we added this tiny interaction created sound in the system. Sound means that there is a collective behavior. You can shake one particle and the sound will propagate throughout the ground state, throughout the excitations of the ground state, which we'll discuss now. So you see that unlike non-interacting bosons and unlike ideal gases, maybe I'll just remind you that the speed of sound in an ideal gas is at zero. Well, in an ideal gas at zero temperature, there is no sound. So it's very different from an ideal gas. This system at zero temperature has collective behavior because of the small interaction, and it has sound. So this is immediate properties of the system that we can predict from the double scaling limit. Next, let's discuss the excitations, because the excitations is what carries the sound. We have to understand what are the excitations above this classical solution, and those excitations is what carries the sound. We can discuss the excitations as classical or quantum particles. It's a weakly coupled system, so you can think about waves around the classical solution as just waves, or you can think about them as created by some Fock space of operators. It's very similar to a free boson or electromagnetism, where we can think about the solution of the Maxwell equations as a field mode, elementary photon, or we can think about it as a classical wave of light, right? So we will find the classical solutions that are excitations of this ground state, and we can then think about them as quantum or classical waves, depending on the context. Are there any questions about the properties of the ground state? That we found that there is sound and some collective behavior? Okay, good. So now we will discuss excitations. We start from our solution and we ask about excitations. And we do a classical analysis of the excitations, and then I'll comment about the quantum meaning of this excitation, these Fock space excitations. It's like in any semi-classical theory. What we do is we try to add to the wave function some small perturbations. I'll pull out the factor of e to the minus mu t. It's very convenient in the expansion in this case. And then we will just have a Fock space or a classical Fourier decomposition of some modes. And I'm just summing over all the Ks. Here, I'm ignoring the boundaries of the container again. I'm just imagining that it's in some large volume, and I can use translational symmetry to diagonalize the excitations into momentum eigenstates. Are there some questions about this Fourier expansion? I'm just gonna have to plug it into the nonlinear Gross-Pitaevsky equation and find the dispersion relation for these modes. So we plug it in back. We plug it in. This is actually an exercise. I wanted to give one exercise today. So one exercise for you is to repeat the calculation of what happens when you plug these modes. You might know if you're interested in black holes. Oh, sorry, how much time do I have? I just want to know that I can finish this exercise. How much?
About 20 minutes, something like that.
Good, great. Actually, this exercise has been revolutionary in physics. It was first done by Nikolai Bogolyubov, probably 70 years ago. No, more, 80 years ago. And this exercise is what led to what we call a Bogolyubov transformation. And that's what Hawking used when he computed the Hawking radiation from black holes. So this exercise is extremely educational. I'll now explain why this exercise became so remarkable. It's just expansion around a stationary solution to the Gross-Pitaevsky equation. but it has a small quirk, which makes it super confusing. So we just plug it in into the equation, and we find a quadratic theory for the fluctuations. So we can write the we can plug it either into the action or directly into the equations of motion. Let me just plug it into the action. Then we get a quadratic action for the fluctuations. And then I can derive the equations of motion from the quadratic action for these fluctuations. So I'll just write the action that you find by plugging it into the... Why is this disappearing? What is going on? That was interesting. So we find some quadratic action with some matrix capital M, curly M. And the matrix curly M, I'll just write the first two entries. It's I d by dt minus h bar by 2m k squared minus g prime by volume. And then there is minus g prime by volume. And then I'll just write it down. I started, so I'll finish. And then there is minus I d by dt. You can check it at home. That's your exercise to see if I haven't made a mistake. Okay. This is the matrix of the fluctuations. And you can then write the equation of motion just by varying. And you can then solve for the time dependence of these fluctuations. This is all super trivial classically. As far as classical physics goes, this is super trivial. I'll just erase the matrix now, so I have more space to write the solutions. So as a classical physics exercise, there is nothing interesting in this. We'll get to the interesting stuff in a second. We just write the action for these waves, and then we found the equations of motion for the waves, and then we can find the time dependence of the waves. So the time dependence of the waves leads to the following frequencies. By frequencies, what do I mean? I mean that the time dependence of these waves is some exponentials, and the frequencies of these exponentials are the following. These are the eigenfrequencies of the system. The frequencies that you encounter are functions of k, and they are given by the following formula. I'll have to explain now many things. This is like the conceptual piece of this whole story. G prime h bar over volume times the mass times k to the power 2 plus h bar squared over 4m squared k to the power 4. So these are the frequencies of these classical modes. I'll put the square root. Okay. And as far as classical physics goes, there is nothing mysterious. These are just the frequencies at which these waves change in time. And there are two limits here. There are two limits that are very important. One is you take low momentum limit. You can take the low momentum limit, or you can take the high momentum limit. In the low momentum limit, we just care about the first term inside the square root, and you get something very nice. Up to factors of pi, you get h bar over mc times the momentum in absolute value. So what is h bar over mc? That's what is xc? Xc is the healing length. So the dispersion relation is linear in momentum. anybody recall ever seeing a dispersion relation that's linear in momentum? Of course, you've seen it in relativistic theories. So the low momentum modes behave as relativistic modes. This is shocking because we started from a Hamiltonian for non-relativistic particles with short range interactions. And then we found that actually the excitations behave relativistically. And what is the speed of sound or the speed of light for these relativistic modes? That's the prefactor in front of the absolute value of k, h bar over mc. That's the speed of sound. You remember that I told you that the speed of sound is proportional to c to the -1 on the previous section. And indeed here we see that the speed of sound is essentially h bar over mc, which has the units of speed. Okay. On the other hand, high momentum particles couldn't care less about this short range interaction, and you get h bar over 2mk squared. And that's it. That's the usual dispersion relation of non-relativistic particles. So what's the physics? We have a quantum ground state, which has some fluid with some pressure and with some waves, and the waves behave relativistically. These are the lowest excitations of the system. And then very high momentum excitations don't see this fluid, they don't see the interactions, they just behave as ordinary Schrodinger particles. That's as far as the classical physics goes. Well, sorry, these are the exact results. There is some quirk about the interpretation. I just wanted to explain the interpretation a little bit. If there are no more, there is a typo here. Just a second. If there are no questions about this, just a second, there is a typo. I need to put M star here. Are there questions about the spectrum of the system and the excitations? Okay, good. So now I'll tell you the most confusing point here. We were studying non-relativistic quantum mechanics originally, and psi was a field operator that destroyed particles, and psi dagger was a field operator that added particles to the bucket or to the container. Now we see that when we write the theory of the fluctuations, these MKs, neither MK nor MK star are creation or annihilation operators. You can ask, what are the creation and annihilation operators? How do you figure out what are the creation and annihilation operators? You have to, by writing the action, you can use the ordinary formalism for finding the conjugate momentum to understand what is the algebra of MK star and MK. So let me just write it for you. Just make space here. Why is this not going away? This guy is resilient to this dot. Okay. So if you do the calculation using the action, you'll find that MK star and MK prime have the usual equal time commutator, which is delta KK prime. But that doesn't mean that MK star is raising operator and MK is a lowering operator. It could be, in fact, more general, and that's the main insight of Bogolubov. Bogolubov just did this exercise, and he wanted to ask, who is the raising operator, who is the lowering operator? The modes are very clear. We have this sound mode, and we have these particles. The question is, how do we create them from this ground state? And Bogolubov made this remarkable observation that we should be able to decompose MK as a combination of raising and lowering operators. So he wrote MKT equals some coefficient VK times a destruction operator. So this operator destroys a particle with frequency omega and momentum k, and some other amplitude u for a creation operator of a particle with the same momentum. So it's ak dagger e to the minus I omega t. So what did Bogolubov say? He said that if you actually solve for the time evolution of these Fourier modes, you'll find that these are linear combinations of exponents. Some exponents oscillate with positive frequency and some exponents oscillate with negative frequency. The frequencies can be easily calculated. This is what this formula tells you. But the fact that each of these modes by itself is neither exponent e to the I omega t or e to the minus I omega t means that they're actually linear combination of creation and annihilation operators. Because the creation operators have to oscillate with e to the minus I omega t, and the annihilation operators oscillate in the opposite way. And you can just, by requiring that creation and annihilation operators have a commutator which is 1, we obtain the following constraint. We obtain that vk squared minus uk squared have to be 1. That's a condition on the Bogolubov decomposition to make sense, so that the commutator is preserved. And you can do a small exercise at home. That's essentially exercise 1. You can try to understand what is the amplitude of mk to be a creation versus an annihilation operator. This is like calculating the vk's and the uk's. That's famously what Hawking did when he calculated the black hole radiation. So what is the point here? The point here is that we started from psi being an annihilation operator for particles in the fluid. But creating a wave on the fluid is not like adding a particle to the fluid. It's like a mixture of adding a particle and killing a particle. It's some kind of linear combination of the two. And these are the eigenmodes of the system. And they have a dispersion relation that's linear and not quadratic. One modern way of saying what's going on here is that the fluid, which is the ground state, this e to the minus I omega t, breaks in one particle symmetry spontaneously. And you can think about those guys as the Nambu-Goldstone bosons of a spontaneously broken U1 symmetry, particle number symmetry. So the particle number symmetry is said to be broken by this ground state, the fluid. That's a semi-classical limit, yes? In the semi-classical limit, we say that the Nambu-Goldstone boson, that the U1 symmetry is spontaneously broken by the ground state, and the excitations have this dispersion relation. And that's why the decomposition of the field operator, which was initially an annihilation operator, contains a linear combination of annihilation and creation operators. And that was the insight of Bogolubov that then Hawking used for black holes. But you see that the origin of this is in the theory of just sodium atoms interacting weakly. Now, I, of course, have to say that now we call this phase of matter superfluid. So nowadays we call this object a superfluid. A superfluid has several properties that we've seen today. One is that it has a speed of sound, so it's a collective it has collective behavior. Second, it has excitations which are linear in momentum, and they move at the speed of sound. Third, there is a spontaneous breaking of U1 symmetry in the sense that the field operator is a mixture of creation and annihilation operators. And there is a Bogolubov transformation. So everything I told you today is essentially the foundations of the superfluid. We see that sodium atoms weakly interacting become a superfluid. So classically, they're an ideal gas. Quantum mechanically, they're a superfluid. And that's essentially the bottom line of the discussion today. That we gave an approximate solution of the Hamiltonian at large quantum numbers, where there are 100,000 sodium atoms in the trap. And we found all these emergent properties. So that is the idea of today. Tomorrow I'll talk a little bit more about this theory, about some excitations which are not just waves. Here we described excitations which are just small waves, but there are some other excitations that I need to explain in preparation for the lectures on conformal field theory.
Sir,
Yes, are there any questions now?
I have a question.
Yes.
To get the excitations about around the ground state, the ground state we have as e to the power of minus I mu t divided by the root of volume.
Yes.
Could we do a Taylor expansion around the coordinates to get the first excitations
A Taylor expansion around where?
around the coordinates?
What do you mean Taylor expansion around the coordinates? Could you explain?
I mean around a fixed value, like t around a fixed value t naught.
You want what you see that the Taylor expansion I didn't do a Taylor expansion. I just assumed that, let's say that on top of this ground state there are some momentum k modes.
But to account for those fluctuations, is it possible to do a Taylor expansion around the coordinates?
You'll have to tell me what you mean by Taylor expansion around the coordinates. Do you mean that instead of choosing exponentials, I should choose like powers, like x to the power second, x cubed, or something like that?
Yes.
No, but usually when we ask about the excitations of a system with translational invariance, it's convenient to look at excitations which are at a given momentum because we know that the momentum operator commutes with the Hamiltonian. So it's a very convenient basis of functions to use the exponentials if we want to
Okay.
study small excitations.
Okay. And one more question. Uh, we needed the ground state to vanish at the boundary of the container.
Yes, I did not take any of that into account. What this will do when you try to solve the problem more fully is that it will change the classical solution a little bit. It will change the mode expansion a little bit, and it would quantize the allowed values of k. You would essentially have to choose the k's which are like in the atom, the k's that have the integer number of modes inside the sphere. It would just quantize everything. If you take this container to be huge, then what I said becomes basically exact.
Okay.
If you want to solve it in a finite container, then you'll have to solve some nonlinear equations and you'll have to find some modes and quantize them. It can be done on the computer, but qualitatively, it will just make the space of k's discrete, which given by some integer divided by the size of the container to leading order.
Okay. Thank you. Yeah.
Yes. Somehow this is a technical point. The conceptual points are the spontaneous breaking of U1 symmetry, the emergent collective behavior, the speed of sound, and the linear dispersion, and the Bogolubov transformation from annihilation operators to creation operators. These are the deep points in this discussion. Yes. Yes. Any other questions?
I just wanted to ask if you could explain again what is the explanation behind having this linear dispersion relation?
Well, here, if you do the exercise that I gave you, you would see that if you expand the action around the classical solution and you solve for the frequencies, you'll get the square root formula that I wrote. And at small momentum, it has linear dispersion. Of course, we started from a Schrödinger problem where all the dispersion was quadratic. But the emergent behavior and the interactions among these 100,000 particles led to some interesting excitations of the Schrödinger problem, which have linear dispersion, collective excitations. You're asking if I can explain where it came from or a technical
Yes.
question?
Like I do understand the computations, but I didn't understand like why this is intuitively reasonable.
It's somehow because now there is sound waves. Unlike ideal gas, where if you start shaking in an ideal gas, if you start shaking one particle, the other particles couldn't care less because there is no they don't see that. But at zero temperature, when you start shaking the particle in one area, the wave functions have some small overlaps, and this signal becomes propagating. And because there is a propagating signal, you get a linear dispersion relation because the signal has a typical speed. Like you remember that the speed of the group velocity is the derivative of the frequency by the wave number k. And that's why you get a linear formula at very small k. It means that at very small k, there is like group velocity to the signals in this fluid. And the group velocity is h bar over mc. It's an emergent collective behavior. It's a purely quantum effect that that affects 100,000 particles. So it can be seen in macroscopic systems.
I see. Thank you.
But you have to go to a zero temperature, yes? So the experiments are done at like 1 Kelvin or 2 Kelvin. You have to go to super low temperatures to see this behavior. Any more
The
questions?
curiosity. Can you hear me? Yes.
Yes.
No, I was wondering if, since you said that the low mode excitations they should be understood as the Goldstone bosons of the broken symmetry, the fact that for high K you go back to the original particles, is it in any sense related to the Goldstone equivalence theorem from QFT? I mean, does it make sense? Is it something that somebody thought about?
It's a very, very good question. It's a very, very good question. Uh, I cannot. Well, what comes to mind to me is that in the context of particle physics, people were inspired by this computation. As you know, in particle physics, there are pions. These are the Goldstone bosons of chiral symmetry breaking in QCD. And inspired by this computation that I showed you today, there is a lot of papers in QCD community asking if maybe very heavy excitations of QCD vacuum, very heavy excitations of the QCD vacuum, kind of go back to normal quantum numbers, and the spontaneous breaking of chiral symmetry is not visible anymore. So what I mean precisely is that somehow very heavy excitations of the QCD vacuum will be in a linear multiplet of the chiral symmetry and not in a non-linearly realized multiplet. Okay, so it's basically the same question. If you go to high excitations, do you just not see the QCD condensate? Right? That's your question essentially.
Yes.
And unfortunately, there were lots of papers on this field, but it doesn't seem, I mean, I'm not convinced that it works. I'm not convinced that it works. So I don't know what it might be just that in weakly coupled systems, the high excitations don't see the condensate. I don't think that's true in QCD. And I don't think that it's a general theorem. That's my opinion now.
Thank you. No, mate, it was just curiosity. I mean, I didn't expect any question, any answer. Thank you.
Last question.
Oh,
Sorry, I'm just a
just a
bit
second.
confused about the
Just a
initial.
second, I made a
Oh,
typo.
sorry.
I
Sorry.
just now saw, I was thinking about that and I saw that there is a typo here. There is a minus sign missing. Because these are the daggers, so they have to have minus K. Yes, I'm listening.
Yes. So I'm just a bit confused about the initial setup. How will you take the large N limit while keeping the gas dilute?
While keeping what?
While keeping the gas dilute, like low density, well high.
No, we
And
don't do that. We don't do that. What we
oh,
do is we keep the healing lengths fixed, if we could do that. We take the large N limit in a fixed trap while keeping the healing lengths fixed. Now, if you look, what does it mean in terms of actual atoms, like the sodium that I gave you? It means that the sample is extremely dilute. You saw that the density was only 10 to the 20 in the meter cubed. Let me ask ChatGPT how many molecules of gas are there in a meter cubed. Can somebody check? I don't have my phone here. So it's extremely dilute, and it's, uh, it's just that in real life, the gases which seem to obey the equations I showed you are in practice with a small density and the very short range interaction. In principle, this formalism applies also if the density is kind of large, as long as the healing length is fixed. So the formalism doesn't break down in any way. As long as the healing length is fixed in the large n limit, the formalism makes sense.
Okay,
It's just
okay, I
that
see.
it's just that when this formalism is compared to nature, to experiments in cold atoms, it works best for dilute systems.
Right.
Because if the system is not dilute, the healing length will become if the system is like if you take the number of particles to be very, very large and you don't make A to be small at the same time, if you keep A fixed, then essentially the healing length will go to zero or something, and it will not be a good large n limit. People want C to be, yeah, so it's a double scaling limit, which makes sense only if C is fixed in the large n limit.
Yes, yes, I see. So yes, okay, thank you.
Can somebody check how many particles are there in a meter cubed in room temperature? How many?
It's 10 to the 25.
Okay, yeah, so it's 100,000 more dilute than the gas in the room, which is good. It justifies the name dilute. Yeah.
Yeah, I had a question about intuitively speaking, even before we did this calculation, should we have expected a large n saddle point to exist for the system? Like, or rather, my question is like, how do we know beforehand whether a saddle point should exist for a large n interacting system?
Oh, it's a it's a it's a self-fulfilling prophecy because if for some system it works, then there are papers about it. If it doesn't work, nobody writes a paper about it. So by
I
definition, every
see.
time you
Okay.
see something like that in the literature, it means that it worked.
Okay. Okay. Fair enough.
Hi, on this model we just saw, is there any other possible realization of this double expansion? Instead of taking the healing length fixed, are there any other realization of this double expansion?
Yes, there could be. Yes. It's possible that I don't see how at the moment. I don't see how at the moment, but it's possible that there are other expansions that work. It's possible. I'm not gonna discount that. Yeah, I'm not gonna discount that. It's possible that there are other good expansions. It's
Okay,
just
so
that this expansion I like because it's very rigorous. And starting from that, you can just derive results and then you can try to compare them to nature.
okay, so perhaps we can also leave some of the questions for tomorrow, and so we'll go on and have the gong show. So thanks, Zohar. And
Thank you. See you
so we
tomorrow.
can use the same link for tomorrow. Thanks.
Thank you. See you tomorrow.
Thank you, Zohar.